Hi, this is Sir Amboy, and welcome again to my lecture series in differential equations. In this episode, I will discuss first-order equations having homogeneous coefficients. But, when are the coefficients of a first-order equation homogeneous? The answer to that question we will discover in the next slide. So, let's begin our discussion. The first-order differential equation in the form m of xy dx plus n of xy dy equals 0. So we may recall that this is called the differential form of a first-order differential equation. This differential equation is said to be homogeneous when m, the coefficient of dx, and n, which is the coefficient of dy, are both homogeneous functions of the same degree in x and in y. So, when is a function said to have homogeneous degree in x and y? A function f of xy is homogeneous, having degree n in x and y, provided that f of kx, ky is identical to k raised to n times the original function f of xy. So if this relation is satisfied, then we can say that the function f of xy or these coefficients are homogeneous, having a degree n. If we can satisfy this relation. But what is the meaning of this relation? Now, to make it simpler, I'd like to say that the equation is homogeneous if the sums of the coefficients for each term in the equation are all the same. This is another way of stating this somewhat complicated expression. So if you cannot comprehend this expression, it's okay. Hindi mo ikamamatay yun. Ano? So ang ibig lang niyang sabihin, kapag daw ang sum ng mga exponents sa bawat isang term, lahat ay pare-parehas, ang equation ay homogeneous. Now, to illustrate this, let us have an example. We have the differential equation 2xy dy plus the quantity x squared minus y squared dx equals 0. So here, the coefficient of dy is 2xy. What is the sum of the exponents in this term? So x has an exponent of 1. And y has an exponent of 1 also. So if we add the exponents here, the sum of the exponents on the first term is 2. So we write it down. The sum is 2. Here on the third term, the only exponent is 2. So here, on the third term, the only exponent is also 2. Okay. So since all the terms have exponents whose sum is 2, then we can say that this differential equation is homogeneous with a degree of 2. That's simple. Ganun lang kadali, no? Adin mo lang ang exponent ng x at y sa bawat isang term. Pag lahat ng terms, ang sum ng exponents ay pare-parehas, kagaya nito, lahat ay equal sa 2, then siya ay homogeneous na ang degree ay equal sa 2. Diba? Napakasimple nun. Sobrang simple lang. Okay? Dahil dyan, let us try kung naintindihan ninyo yung concept ng pagiging homogeneous. So here, which of the following equations is not homogeneous? Not homogeneous. So here, we have the following choices. A, y squared minus xy dx plus x squared dy equals 0. So let us inspect if this equation is homogeneous. The first term, the only exponent is 2. On the second term, the sum of the exponents is 2 because 1 plus 1 equals 2. And in the third term, the exponent is 2. So, the sum of the exponents in each term is equal to 2. So, this must be homogeneous with a degree equal to 2. How about the next one? Y prime equals, so here, in the numerator, the exponent of x and y are both 1. So, the sum is equal to 2. Let's write. So, here, ang sum niya ay 2. Dito naman, 2 talaga. Ito naman 2 din. So, this must be homogeneous with a degree of 2, just like the first one. Let's try the third. So, for the first term, the exponent of x is 2 and the exponent of y is 1. So, here, the sum of the exponents is 3. So, here, we have only y raised to 1. And here, we have x raised to 3. So, They are not the same. Why? Because two terms have the sum of exponents equal to 3, while one term has its exponent equal to only 1. So, this equation is not homogeneous. So, this must be the correct answer because we're looking for the one which is not homogeneous. Now, let us see if the fourth one is homogeneous. So, for the first term, the sum of the exponent is 3. The second term is also 3, and the last term we have also 3. So, it's homogeneous with a degree equal to 3. That's it. So now, we already know how to tell if a first-order equation is homogeneous. Our next goal is to actually solve equations having homogeneous coefficients. Okay? Let us solve example number 2. Solve the equation y squared minus xy dx plus x squared dy equals 0. So, how do we solve first-order equations having homogeneous coefficients? So here, we use change of variable. For example, we will let y be equal to a certain vx. And if I replace y with vx, I will also have to replace dy with the derivative of this. So, since both are variables, we will apply the derivative of a product, v dx plus x dv. Or, another representation is to replace x. Instead of replacing y, we can replace x with vy. So, if we replace x with vy, I will also have to replace dx with v dy plus y dv. Just like what we did in the first case. So, sir, which representation are we going to use? Is it y equals vx or x equals vy? So it depends. Anyway, either of them will give you the correct answer. But of course, we are used to solving a problem using the solution that is simpler. So which of these two would result to a simpler solution? So it depends again on the problem. Okay? So if we solve this problem now, we will see. Okay? So let us solve. Sir, which are we going to use? Is it y equals vx or x equals vy? Now remember, if you replace y, you have to replace dy. And if you replace x, you will also replace dx. But both dy and dx will be replaced by two terms. So either you use dy or dx, the resulting substitution would have two terms. So it would be better if, in this case, we will replace dy. Because dy, when we replace it, would be equivalent to two terms. And we multiply it to a single term there. But if we replace dx, we will replace dx with two terms and multiply it to another two terms. So that would be more complicated. Now, let us do the substitution. I replace y with vx, so y squared will become v squared times x squared minus x times y. Again, you replace y with vx, so vx times another x there, so vx squared, and then I enclose them in a parenthesis and multiply them by dx. Plus, here I have x squared, and I will replace the dy with v dx plus x dv. And then, equal to 0. So now what is the next step? The next step is to combine like terms. So here we have three terms whose multiplier is dx. 1, 2, and 3. So we combine them. V squared, x squared, minus v x squared. And then here we have plus v x squared. And then we multiply them by dx. And then plus, okay, the lone term containing dv would be x cubed dv. X cubed dv. And then equals 0. Now, if we can simplify, then simplify. Okay, so here, we notice that these two terms will cancel each other. because one is positive and the other is negative. Okay, so here on the left side, we are left with v squared x squared multiplied by dx and then plus x cubed dv equals 0. So again, if it's possible to simplify the expression and cancel the common factor. So here, the common factor is x squared. That's why it will be cancelled. And here, we will be left with only x. Okay, so rewriting the equation, the simplified equation, we will get v squared dx plus x dv equals 0. So now what can you say about this equation? So notice that this equation is now separable, right? Okay, so if you notice, the equation that we obtained here is now separable. So that is the reason why we used a substitution technique. We used the substitution y equals vx in order to make the equation separable. And now that the equation is separable, we can solve the differential equation. Separating the variables, we will get dx over x plus, here we will have dv over v squared equals 0. So now the next step is to integrate both sides, and here we will get ln of x plus, okay, so to integrate this can be written as a v to the negative 2 dv. And if we integrate this would result to v to the negative 1 over negative 1. V to the negative 1 over negative 1. And then on the other side, we'll get the arbitrary constant c. So here, we will get ln of x minus 1 over v equals c. Now, we will use back substitution because the original variable is not v. Rather, it's y. Okay? But since our representation is this, y equals vx, v is y over x. So I can replace this v here with y over x, and I will get ln of x minus 1 over y over x is just x over y equals c. And then after that, I do some algebraic manipulation. Ln of x minus c equals x over y. And after that, I solve for y. So now y equals x over ln of x minus c. So you can use either ln of x minus c or ln of x plus c. After all, it's just an arbitrary constant. So, guys, the expression that we have here is our general solution. Okay? So, as you have noticed, this is more challenging than solving separable differential equations. So, let us now solve the third example. Sir, I have a question. During exams, it's not stated whether the equation is homogeneous or separable. So how do I know which method to use? Okay, so first, you have to inspect if the equation is separable. Okay, let us look at this differential equation. Can we separate the variables x and y here? Okay, so if the function multiplied to dx is a product, it's easy to separate x and y like this. So here we have x and y as a product, but here we have x and y as a sum. Rather, naka-minus yan. Okay? So if there is a sign in between them, so if it's not a product, then it's difficult to separate them. So the instinct is to see or try if the equation is homogeneous. Okay, look at the first term. So here, the sum of the powers or exponent is 2. Here, the exponent is 2, and there, the exponent is also 2. So now, the equation is homogeneous. It's not separable, but it's homogeneous. And we already know how to solve homogeneous equations. What substitution are we going to use? Are we going to use y equals vx or x equals vy? Again, that depends on the problem. So you should look at the differential dy and dx. And see, here, dy is multiplied only to a single term, 2xy. But here, dx is multiplied to two terms. So the simpler solution would be to use y equals vx. Because if I replace dy with two terms, I will simply multiply it to this term, rather than multiplying two terms to another two terms. So let's use y equals vx. So let us substitute 2x times y, which is vx, and then dy. If I replace y with vx, then dy would be v dx plus x dv. So I just copy v dx plus x dv. Okay. And then plus, here we have x squared minus y squared. So v squared times x squared, and then dx equals 0. So let us now simplify and combine all the terms containing dx. So what are the terms containing dx? So here we have 2x squared v squared dx, and then plus this term x squared also dx minus v squared x squared. Okay, and then all of them will be multiplied by dx. And then here we have a lone term containing dv, so that will be 2x. So we have 3 x's, so 2x cubed times v. dv equals 0. So if it's possible to simplify, simplify. Other terms which will cancel. So here we have 2x squared v squared and another v squared x squared. So we will get x squared v squared plus x squared times dx plus 2x cubed v dv equals 0. Now let us see if there is a common factor which we can cancel. So here we have 3 terms whose common factor is x squared. If you have noticed, x squared is common to all the terms. So we can cancel x squared. There. So dito matitira 1. Dito matitira x na lang. Okay, so let us rewrite the simplified expression. So here, we will be left with v squared and then plus 1 dx plus 2. Here, we have x multiplied by v dv equals 0. Ay, magkaiba pala ng kulay yung green. Okay lang. So now, what have you noticed in this final equation that we have here? So this is now separable. Okay, and we can now separate the variables dx over x, and then here plus 2v dv over v squared plus 1 equals 0. So the next step is to integrate. So we can obtain the general solution. Integrating both sides, we will get ln of x plus. Okay, so here I will use the substitution method and replace v squared plus 1 with u. And if I let this be equal to u, my du would be 2v dv. And that's exactly what we have in the denominator. Thus, I can express this as du over u, which when I integrate would be equal to ln of u. Okay. Now, on the right side, we would have the arbitrary constant. But since on the left side, both terms contain ln, then it would be better if the arbitrary constant on the right would also have an ln. So it would be easier for us to simplify our general solution. Now, we will replace u with v squared plus 1. So, ln of x plus ln of v squared plus 1 equals ln of c. So, this is where we will obtain our general solution. Okay, so let's proceed to the next slide to continue our computation. I'll just copy-paste the expression that we have obtained in the previous slide. So here we have ln of x plus ln of v squared plus 1 equals ln of c. So we can apply the properties of logarithm. The sum of two ln's could be expressed as the ln of a product. So I can write this as ln of x times v squared plus 1 equals ln of c. So since here we have ln on both sides, we can eliminate the ln by raising both sides of the equation to e. And by doing that, we will be left with x times v squared plus 1 equals c. Okay. Now we will use back substitution. Remember that we used the substitution that y equals vx. So we have to replace v here with y over x. Okay, so that will be v squared. Okay, so that would be y squared over x squared plus 1 equals c. So I can simplify this by having a common denominator, x squared, right? And here I will have another x squared equals c. Now, the x here will cancel. And the 1x will be left on in the denominator. And to simplify, I can multiply both sides of the equation by x to eliminate the denominator x here. So on the left side, what will be left is just y squared plus x squared. And on the right, we will have cx. Okay? So this now represents our general solution. Ayan, tapos na tayo. Ito na yung general solution mo. Ngayon, kung napansin mo, we have here an equation in the form x squared plus y squared. This is an arbitrary constant. So, kapag inilipat ko yan dyan, kahit positive yan, okay lang. Plus cx equals 0. And if you remember, this is a conic section. Okay? This is a conic section, right? So, this general solution represents a family of curves. What family of curves is represented by a conic section whose equation is x squared plus y squared plus cx equals 0. So, it's a family of circles. Okay? So, this is the family of circles represented by this general solution. So, we have circles whose centers are along the x-axis and they are tangent to the y-axis. Okay? So, this is a family of circles whose centers are on the x-axis and are tangent to the y-axis. So that's the proper way of describing this family of curves. Okay? So, next example, example number 4. Solve the equation xy prime equals x plus y. So, it's better if we will write this expression or differential equation in its differential form by multiplying both sides by dx. So, we will get x dy equals the quantity x plus y dx. Okay. So, the equation is homogeneous with a degree equal to 1. So, now let us use substitution. Am I going to use x equals vy or y equals vx? It depends on the multiplier of dy and dx. Since here, the multiplier of dy is just x, it's better to use y equals vx. So we will replace y with vx and replace dy with v dx plus x dv. Now, x, then dy will be replaced with v dx plus x dv equals x plus here, y will be replaced by vx and then the multiplier dx. The next thing is to simplify. So we have 3 terms containing dx, right? 3 terms containing dx. So we combine all the terms with dx on the right side and leave all the terms containing dv on the left. So we will have x times x is x squared dv. That's equal to, here we have x plus vx, and then this term, x and then x times v is negative vx, and then all of them will be multiplied by dx. Ay! Shit! Napansin mo ba yon? Did you notice this? They will cancel. And what will be left is x squared dv equals x dx. And x is a common factor, so we can divide both sides of the equation by x, leaving us with x dv equals dx. So we just separate the variables. dv equals dx over x. And after we have separated the variables, we integrate both sides. Integrating both sides, we will get v equals ln of x, of course, plus c. Again, use back substitution. V should be replaced with y over x. So y over x equals ln of x plus c. So we can multiply both sides of the equation by x. So we will get y equals x ln of x plus cx, or y equals x times the quantity ln of x plus c. Okay, so this is this is simpler compared to this. Okay, so this is now our general solution. Okay, this is our general solution. O, di ba? Ang dali lang? Sobrang dali. Walang kasing dali. Okay, let's solve the last and final example for this topic. Solve the equation x times ln of x minus ln of y times dy minus y dx. Okay, so if we inspect, this equation is homogeneous with a degree of 1. And this time, instead of using y equals vx, we will be using x equals vy. Why? Because here, dy will be multiplied to this term, while here, dx will be multiplied to only y. So it would be simpler if we will replace x instead of y. Okay? But before that, we can actually simplify this. Applying the laws of logarithms, we can use the property of ln of x minus ln of y equals ln of x over y. Okay? So let's rewrite this. X times ln of x over y multiplied by dy minus y dx equals 0. Now, we use the substitution x equals vy. So here, I will replace x with vy. And here, I have x replaced by vy also. And I just copy the denominator y. And then I multiply them with dy. And then minus y. And then multiplied by dx. So since I replaced x, I will also replace dx with v dy plus y dv. And then equals 0. So if it's possible to simplify, then simplify. So here, y in the denominator and in the numerator will cancel, leaving us with Vy times ln of V multiplied by dy minus y times v dy plus y dv equals 0. So let us now combine like terms and simplify this equation. So here we have two terms containing dy and only one term containing dv. Okay, notice also that vy dy is common to the first two terms. And that means it's a common factor. So vy dy times here, we have ln of v minus, this entire term is our common factor. So minus 1. And then minus y times y is y squared multiplied by dv equals 0. Now, if it's possible to simplify this further, okay, we can simplify. Notice that y is a common factor. So we can cancel y here and we will be left with only a single y here. Okay, let us rewrite the simplified expression. We have v dy times ln of v minus 1 minus y dv equals 0. Okay, so you may notice that this equation is now separable. And because it's separable, we can now solve the differential equation. So let me just copy this equation on the next slide. And after that, we can proceed to the separation of variables. Okay. So here it is. We have v times ln of v minus 1 dy minus y dv equals 0. So we now separate the variables v and y. So here I will get dy over this y and then minus, here I will have dv over all the terms containing v. So that's v times ln of v and then minus 1 equals 0. So the next step is to integrate the equation so that we can get the general solution. Okay, it's easy to integrate this. This will give us ln of y. But how about this term? Okay, if I let the ln of v be equal to u, ln of v minus 1, then my du will be dv over v, and this term will be 0 because the derivative of a constant is 0. And notice that here we have dv over v, and there we also have dv over v. And here I can replace this entire ln of v minus 1 with u. Thus, I can use substitution method and write the equation as dy over y minus du over u equals 0. So I can now integrating, I will get ln of y minus ln of u equals, so since we have ln's here, I will also use ln with the arbitrary constant. I can write this as ln of y over u equals ln of c. And then after that, I can raise both sides of the equation to e. So I can eliminate ln and write y over u equals the arbitrary constant c. So now to solve for y, so I can multiply c by u. However, u is equal to ln of v minus 1. So that will be c times ln of v minus 1. But this is not yet the final answer because the original variable is x instead of v. Okay, but remember we used the substitution v or x rather equals vy. So from this, I can replace v with x over y. So y equals c times ln of v again is x over y minus 1. Okay. So I think it would be better if I can write this as a single line. Again, applying the properties of ln, I can rewrite the general solution in this form. Y equals the arbitrary constancy times ln of x minus ln of y minus 1. Okay. So this is a good looking general solution here. Okay. This is our general solution. Okay. So that's it. We're done with solving equations with homogeneous coefficients. So let us have a recap. In solving equations with homogeneous coefficients, first, we will use the substitution y equals vx, or possibly this, x equals vy, depending on which of the two would be more practical. And then after that, we simplify the expression in order to make the equation separable. Once the equation is separable, we can now separate the variables and integrate. After integration, you simplify and obtain the simplified expression for the general solution. That's it. Okay, so our next topic will be solving exact differential equations, and that will be discussed in the next episode. Okay, so see you. Bye.